NASA expected Titan to be just another icy moon, a frozen world buried under haze. What they found instead looked unsettlingly familiar. Beneath that thick orange sky are rivers winding across valleys, lakes glittering in the dim light, seas larger than our Great Lakes, and storms that pour liquid back into them. It's the only other place in the solar system with stable liquids on its surface, and that alone makes it extraordinary. Yet the more NASA studies Titan, the more it refuses to fit the rules. For most of history, Titan was just a blur. Even with our best telescopes, all we saw was a hazy orange ball, its surface hidden behind layers of smog. That haze was so thick that it blocked almost all visible light, leaving Titan as one of the most mysterious places in the solar system. Scientists could measure its size, a diameter of about 5,150 kilometers, larger than the planet Mercury, estimate its density, and know that it was Saturn's largest moon, the biggest among the gas giant's 274 known satellites. But beyond that, the details of its surface were guesses. Some thought Titan might be covered by a global ocean. Others imagined it as a frozen wasteland. The truth didn't begin to emerge until spacecraft got close enough to actually look beneath the haze. Titan orbits Saturn at an average distance of about 1.22 million kilometers, and together they lie roughly 1.4 billion kilometers from the Sun. The first breakthrough came in 2005, when the European Space Agency's Huygens probe detached from NASA's Cassini spacecraft and began its descent into Titan's atmosphere. It was the first time a probe had ever landed on a moon in the outer solar system. For more than 2 hours, Huygens fell through Titan's orange skies, parachutes slowing it down while cameras and instruments sent back data. The pictures it transmitted as it dropped were astonishing. They revealed bright highlands and dark channels that looked like river valleys, winding and branching just as rivers do on Earth. When Huygens finally touched down, the first images from the surface showed something completely unexpected: rounded pebbles scattered across the ground. These weren't jagged shards of ice or rock. They had been smoothed as if by flowing liquid. Scientists immediately recognized what they were seeing: evidence of erosion, the kind that happens when material is carried and tumbled by moving fluids. On Earth, rivers polish stones into smooth shapes over time. On Titan, the same process had happened, except with liquid methane or ethane instead of water. That single image proved that Titan's surface had been shaped by active processes, not just frozen in place for billions of years. But Huygens could only send pictures from one small landing site, and it didn't last long. That's where Cassini's instruments came in. Orbiting Saturn for more than a decade, Cassini repeatedly turned its cameras and radar toward Titan. Because visible light couldn't penetrate the haze, Cassini used radar imaging to map the surface. The results were unlike anything anyone had imagined. The radar images revealed enormous dark patches near Titan's poles that were smooth and flat, exactly what you would expect if they were filled with liquid. Still, scientists needed confirmation. That confirmation came in 2009 in the form of one of Cassini's most famous pictures, the sunglint image. Cassini's camera caught sunlight reflecting off the surface of one of Titan's northern seas, just like sunlight sparkles on a lake here on Earth. It was the smoking gun, proof that those dark patches weren't just flat ice or solid ground. They were seas of liquid methane and ethane. For the first time, humanity had proof that another world had standing bodies of liquid on its surface. Cassini's radar maps didn't stop there. They revealed the outlines of enormous seas such as Kraken Mare, Ligeia Mare, and Punga Mare. Kraken Mare alone is larger than all of North America's Great Lakes combined. Radar also measured depths, and in some places, Kraken Mare was found to be more than 100 meters deep, possibly much more. That means Titan doesn't just have puddles or shallow lakes. It has deep, vast seas, capable of holding staggering amounts of liquid hydrocarbons. And it wasn't only the polar regions that surprised researchers. Cassini's radar swaths across Titan's equator uncovered something else: endless dune fields. These looked like parallel dark lines stretching for hundreds of kilometers, broken only by mountains or highlands that redirected their paths. The dunes were made not of sand as we know it, but of tiny grains of frozen organic material, built up from the constant chemical fallout produced in Titan's atmosphere. Winds carried these grains and piled them into massive dune seas, making Titan look in some regions like a desert world despite its frozen temperatures. One of the most valuable aspects of these images is how much they reveal about Titan's surface processes. The river valleys in the Huygens images told us that erosion and liquid flow had shaped the land. The sunglint image proved seas really exist, showing Titan's methane cycle is active today. The dune maps revealed an atmosphere capable of producing steady winds strong enough to transport material over long distances. And the depth measurements of Kraken Mare proved that Titan's methane cycle isn't a thin surface feature, but a global-scale system with reservoirs deep enough to rival Earth's own great bodies of water. Together, these images transformed Titan from a hazy mystery into a place with landscapes we could recognize, even if they were built on alien chemistry. They showed us a world where rain falls from the sky, rivers cut valleys, dunes march across plains, and seas spread across polar basins. Each picture was a direct window into processes that were once only theoretical. Without those images, Titan would still be guesswork. With them, it became real. A place we could actually picture standing on, even if it would be the strangest shoreline or desert anyone has ever seen. What sets Titan apart from almost every other moon is that it doesn't sit bare and exposed in space. It's enclosed in a true atmosphere, thicker and heavier than Earth's, a blanket of gas that makes it feel more like a small planet than a satellite. Standing on Titan's surface, you would feel the weight of the air pressing on you with about 50% more pressure than at sea level here on Earth. That's remarkable for a moon, because most moons can't even hold onto an atmosphere at all. This atmosphere is what gives Titan its signature look. From the outside, all we see is a smooth orange ball. The haze that hides its surface is produced high above, where sunlight interacts with the gases present, mainly nitrogen and methane. Particles form and clump together, creating reddish-brown organic aerosols known as tholins that scatter blue light and give the moon its distinctive hue, eventually settling down through the atmosphere and creating a permanent smog. For scientists, this haze isn't just a nuisance that blocks our view. It's evidence of ongoing complex chemistry. Molecules are constantly being broken down and rebuilt into heavier organics. Over time, they accumulate and fall, coating Titan in a steady drizzle of material. Another striking feature is how the atmosphere moves. It doesn't simply rotate in sync with the moon below it. Data from Cassini showed that winds high in Titan's skies can race ahead of the surface, creating what researchers call superrotation. This means the upper layers of air complete a lap around the planet faster than Titan itself spins. In fact, while Titan takes about 16 Earth days to rotate once, its upper atmosphere can circle the entire moon in just about 1 Earth day, driven by powerful zonal winds reaching up to 200 meters per second, roughly 16 times faster than the moon's surface. It's not the kind of behavior you'd expect from a distant, frozen world, and it tells us Titan's climate system has its own strange rhythm, one that scientists are still working to understand. There's also the matter of Titan's seasons. As Saturn orbits the Sun, Titan tilts and shifts in ways that change how much light each hemisphere receives. These subtle differences are enough to set patterns in motion, building circulation cells in the atmosphere that shift over time. Cassini observed cloud systems forming in one hemisphere, growing larger and then slowly fading as the seasons changed. The cycle repeats as sunlight favors the opposite side of the moon. Titan may be far from the Sun, but even that faint energy is enough to drive a cycle of shifting weather. The James Webb Space Telescope recently added another layer to this story. Using its powerful instruments, Webb detected unstable molecules in Titan's atmosphere. Molecules that can only exist briefly before reacting into something else. In late 2022, during one of its first observations of Saturn's largest moon, Webb identified methyl radical, an extremely reactive carbon-based molecule never before seen so clearly on Titan. This compound is thought to be a key intermediate in the formation of more complex organic molecules. Spotting them in place means we're catching the chemistry mid-step. Instead of seeing only the haze that eventually forms, scientists are now able to observe the individual reactions as they unfold. It's the clearest evidence yet that Titan's skies are not static. They're alive with activity. What all of this shows is that Titan's atmosphere isn't just a shell of gas. It's a working system, dense enough to shape circulation, active enough to shift with the seasons, and chemically rich enough to create new compounds on a constant basis. For a moon this far from the sun, it's extraordinary. Titan's sky is more than a haze that blocks our view. It's a laboratory in itself, one that challenges our ideas about how atmospheres behave in places so different from Earth. When scientists talk about Titan, the conversation always turns eventually to chemistry. This isn't surprising because Titan is coated in organic material from top to bottom. It's in the atmosphere, in the haze, in the dunes, and likely mixed into the lakes and seas. But the key question is whether any of this chemistry could take steps towards something resembling life, or at least the beginnings of it. The most important clue comes from Titan's constant supply of complex molecules. High in the atmosphere, energetic radiation breaks apart simple gases and triggers a cascade of reactions. The result is a steady production of hydrocarbons and nitrogen-bearing compounds. These molecules grow more complex over time, sticking together to form particles that drift downward. What falls to the surface is not random dust, but material rich in carbon and nitrogen, two of the elements most critical for life on Earth. Over geological timescales, this has built up a thick coating across Titan, providing a chemical stockpile unlike anywhere else we've explored. The presence of lakes and seas changes the equation further. These bodies of liquid aren't just passive reservoirs. They provide environments where molecules can dissolve, mix, and interact. On Earth, the separation of chemicals into compartments was one of the first steps toward biology. That's why a recent finding sparked so much excitement. Under Titan-like conditions, simulations show that molecules could spontaneously form structures resembling vesicles. These are small bubble-like compartments with an inside and an outside. On Earth, cell membranes are made of lipids, but on Titan, researchers propose that different molecules, stable in liquid methane, could form similar boundaries. The concept is sometimes called azotosomes. New studies suggest that Titan's active weather, its methane rain, evaporation, and winds, could help these azotosomes form and build up over time. They might even protect fragile organic molecules such as those detected by Cassini and give them a safe space to react and combine into more complex forms. If such compartments can form, even temporarily, they provide a place for chemistry to become more organized. And organization is a key ingredient in the recipe for life. Of course, Titan's conditions are extreme. Surface temperatures hover around minus 180 degrees Celsius, so slow reaction rates are a serious barrier. Life, as we know it, relies on liquid water and relatively warm conditions to allow chemistry to move quickly enough to sustain itself. Titan offers neither, but that doesn't mean it has nothing to teach us. Even without active biology, the chemical reactions taking place there may closely mirror the prebiotic chemistry that set the stage for life on early Earth. In that sense, Titan serves as a laboratory we could never build ourselves, a natural experiment running on a planetary scale for billions of years. The possibility of a hidden ocean beneath Titan's crust makes things even more intriguing. That ocean is thought to be water mixed with ammonia, kept liquid by internal heat and pressure. Unlike the surface, it could be more hospitable to reactions similar to those that once led to life here. If material from the surface ever exchanges with that interior ocean, through fractures or cryovolcanic eruptions, then Titan might host two parallel laboratories, one testing exotic methane-based chemistry at the surface, and another testing water-based chemistry below. For scientists, this dual nature is what makes Titan so valuable. It doesn't just show us one path to complexity, it demonstrates two very different ones coexisting in the same world. By studying it, we're not just looking for life directly. We're testing how flexible the conditions for life might be, how many routes chemistry can take before it turns into biology, and whether what happened on Earth is only one example of many possible stories. This is why Titan has become one of the most important targets in the search for habitability. It pushes us to think beyond familiar boundaries. It forces us to ask whether life really requires the recipe we know, or if it can emerge from ingredients and processes that look nothing like our own. Titan may never host organisms we'd recognize, but it is already showing us that the building blocks of complexity are not confined to Earth. For all the progress made with Cassini and Huygens, those missions could only give us part of Titan's story. Huygens landed once, in one place, and lasted for a few hours. Cassini orbited Saturn for over a decade, but could only study Titan from above. To understand Titan in detail, scientists need a way to explore it directly across multiple locations for years at a time. That's where NASA's next mission comes in. Dragonfly is unlike anything we've sent to another world before. Instead of a rover that crawls along the ground or a stationary lander, Dragonfly is a flying vehicle. It's built with 8 rotors, like an oversized drone, and it's designed specifically for Titan's unique conditions. The dense atmosphere and lower gravity make flight easier there than on Earth. With far less weight to lift and thicker air to push against, a craft that would struggle here can travel long distances on Titan with relatively little energy. This advantage means Dragonfly will not be trapped in one location. It can take off, scout the terrain, and fly to entirely new landing sites, opening up a kind of exploration we've never tried before on another planet or moon. The plan is for Dragonfly to launch in 2028 and arrive at Titan in the mid-2030s. Once it touches down, its first home will be in the equatorial region, known as the Shangri-La Dune Fields. From there, it will gradually expand its range, hopping from site to site. Each new stop will be carefully chosen, giving scientists the chance to compare different kinds of terrain: dunes, icy plains, possible ancient riverbeds, and even the remnants of impact craters. Every location will be studied with onboard instruments designed to analyze chemical composition and surface properties. One of Dragonfly's key goals is to examine Titan's organic material in detail. Cassini and Huygens gave us evidence that complex molecules exist, but they couldn't tell us exactly how far that chemistry has gone. Dragonfly will carry instruments capable of identifying these compounds directly, including mass spectrometers that can sort out chemical structures and determine whether Titan's surface holds molecules that resemble the precursors to life. If Titan's chemistry has taken steps toward complexity beyond what we expect, Dragonfly is the mission that can reveal it. Dragonfly will also investigate Titan's geology. Its ability to fly over long distances means it can reach craters that may expose material from below the surface. These areas are important because impacts can deliver heat and energy, sparking chemical reactions that don't happen elsewhere. By sampling from both dunes and craters, Dragonfly will provide a broader picture of how Titan's surface has changed over time and how its chemistry varies across different environments. Another aspect of the mission is to test Titan's atmosphere and weather directly from the surface. Instruments will monitor wind, temperature, and other conditions as Dragonfly travels. This will give scientists new insight into Titan's climate and how its atmosphere interacts with the ground below. It will also provide valuable experience for designing future missions, since Titan is one of the most promising worlds for continued exploration. What makes Dragonfly especially exciting is the way it expands our approach to planetary science. On Mars, rovers have changed the way we study planets by giving us mobility. On Titan, Dragonfly will push that concept further by giving us flight. Instead of inching along a few meters each day, it can cover kilometers in a single flight, scanning new horizons and then landing for detailed study. This ability turns Titan from a distant world glimpsed in fragments into a place we can explore systematically. When Dragonfly begins sending back its data, it will not only answer questions about Titan's chemistry and geology, but also reshape how we think about habitability in the solar system. If it finds evidence that Titan's organics have organized themselves in unexpected ways, that would force us to reconsider the limits of biology. Even if it doesn't, the mission will provide an unprecedented look at how an alien world can operate with systems that parallel Earth's in form, but not in substance. Dragonfly is more than just another step in exploration, it's an entirely new way of approaching a world. By flying through Titan's skies, landing in multiple places, and sampling materials across a variety of landscapes, it promises to turn speculation into hard evidence. For decades, Titan has been a place of hints and mystery. Dragonfly is the mission that will finally give us answers. After everything NASA has uncovered, Titan no longer feels like a distant, frozen moon. It feels like a complete world, one that forces us to challenge our assumptions about what's possible beyond Earth. The images showed us familiar landscapes, seas, rivers, dunes, yet they're made of entirely different substances. The atmosphere turned out to be dense, dynamic, and chemically active, not thin and lifeless as you'd expect so far from the Sun. Beneath the surface, evidence points to a hidden ocean that could still be influencing Titan's activity today. And the chemistry spread across this moon is unlike anything we've seen elsewhere, hinting at paths toward complexity that don't rely on water or warmth. The significance of Titan is not just in what it is, but in what it represents. It's proof that Earth isn't the only place where natural cycles can carve landscapes and shape climates. Titan shows us that planetary processes, erosion, weather, circulation, internal activity are not unique to our world. They can appear under alien conditions, producing results that look strangely familiar, but operate under completely different rules. That means the search for habitability cannot be limited to Earth-like environments. If Titan exists here, orbiting Saturn, then something like it may exist elsewhere too, around distant stars with very different conditions. This is why Dragonfly matters so much. It isn't just about exploring a moon. It's about testing the boundaries of habitability itself. If Titan's chemistry has taken even a small step toward organization, then it tells us that life doesn't have to look like it does on Earth. If instead the chemistry has remained purely chemical, Titan still gives us the clearest example of how complex prebiotic systems can become without biology ever starting. Either answer changes how we think about life in the universe. In the end, Titan is a reminder that the universe has more imagination than we do. A world cloaked in haze, with seas of liquid methane and dunes made of frozen organics, should not exist according to our simple expectations of moons. And yet it does. As we prepare for the next chapter with Dragonfly, the question is no longer whether Titan is interesting. It's how much more it will force us to reconsider once we finally see it up close, across multiple landscapes, for years at a time.